Right, welcome to lecture 11 from chapter number 8. Today we'll study logical effort. Logical effort is a technique to minimize chain delays. Before this we have studied a general technique to minimize chain delays based on computing threshold derivative and putting it equal to 0. In this lecture we'll analyze logical effort. In the next lecture we'll see how we can use logical effort to minimize actual chain delays. A logical effort has certain components. The first component is named same as logical effort. Logical effort of a gate is the input capacitance of that gate divided by a reference capacitance. Let's see what the reference capacitance is. The reference capacitance is 1 plus R times CGN. It's the input capacitance of a symmetric node with M is equal to 1. In our previous lectures you can find out that the input capacitance of a symmetric node with scaling factor 1 is this. C reference is equal to 1 plus R, where R is the mobility ratio, mu n over mu p, times the gate capacitance of node of NMOS FET, whereas the gate capacitance for PMOS FET is R times larger than that. So this is the expression for C reference. We have computed this and we have derived this expression in our earlier lectures. Right, so coming back to logical effort is the input capacitance, the ratio between the input capacitance of a gate and the reference capacitance. The reference capacitance comes from here. Right, for G naught for a symmetric node with M is equal to 1 would of course be 1, because the input capacitance would be the same as this reference gate, so it would be 1. But for different gates, that would in our upcoming lectures we'll see that for NAND and NOR and other combinations we'll have different G's. Whereas for a chain, G is the product of the individual G's. If we have, for example, n gates in the chain, the logical effort of the chain, this capital G is the logical effort of the gain, whereas this small g is the logical effort of a gate. In a chain we have more than one gates. If we have n gates in the chain, that would be G1 times G2 times G3 up to time Gn. One other concept related to logical effort is electrical effort, and then we'll see how we combine this to find the total chain delay. Logical effort is the second component of this technique. We represent it with small h and capital H. And the small h is for a gate, which is the output capacitance of that gate divided by its input capacitance, and it is defined for a gate. The output capacitance, for example, for this node, the output capacitance would be different than the input capacitance. The output capacitance of course would be the load capacitance. The load capacitance plus the FET capacitance divided by the input capacitance. Right, and for a chain, this small h converts into capital H, and this is also the product for n HIs, means this is H1 times H2 times H3 times Hn. And then comes their combination. The combination is called path effort. Path effort is the combination of logical effort and the electrical effort. This path effort is the third term we use in this technique. Path effort is represented by F, capital F, which is capital G times capital H, where capital G we already know is 1 to n GIs, and capital H is product 1 to n HI. And the delay of the chain involving n gates, so the expression for path delay D is n times F to the 1 over n plus P, where P is parasitic delays. Generally they are negligible. otherwise they are given. If they are not given, we'll assume parasitic delays to be equal to 0, and the expression is t is equal to n times f times n times f to the power 1 over n. Right. To better understand the concept, let's solve an example where we have a knot. The knot is driving another knot, and it is driving a capacitance. The capacitance that the final gate is driving is C3. Both gates are symmetric with M is equal to 1. So what would be the capital G? Capital G is I1 to N, Gi, where N is 2 here, so 1 to 2 means G1 times G2. G1 is the input capacitance of this gate. Since this is symmetric with M is equal to 1, this would have the same input capacitance as the reference gate. The same would be true about the other gate. So the answer comes out to be 1, but it is not always 1. For different gates, we'll see in our later lectures, we'll see that it will be different than 1 for some other gates. Right. What's about H, which is 1 to 2 Gi, G1 times G2. Oh, not Gi, Hi, H1 times H2, where H1 is the output capacitance. Let's see the output capacitance. For first gate, it's C2, where it is C1. For the second gate, the output capacitance is C3 divided by the, so this C2 cancels with this C2, C3 over C1. And in this case, since the first gate is a symmetric knot with M is equal to 1, C1 is C reference. So this is H. So capital G is 1, capital H is C3 over C reference. As a last step, let's compute D, the total path delay. The total path delay is N to the F over 1 over N plus P, where this capital G is a 1 and capital H is 1. Also, capital H is C3 over C reference. So F is capital G times capital H, 1 times C3 over C reference, which is C3 over C reference. So N is 2, F is C3 over C reference times 1 over 2 plus 0, because there is no parasitic delays given. So this is how we can compute delay due to logical effort, using logical effort technique. In our next lecture, we will study how we use this expression to minimize chain delay. Thank you.